Pakistan. So for the participant who are not familiar with Emanuela, so Emanuela is a well-known name in commutative algebra. She's an associate professor specializing in the area of specialized in the area of commutative algebra, and she worked at the University of Genova, Italy, a very exciting place. With more than 20 years experience, she has been deeply involved in teaching and supervising both school and university educators. Emanuela has a notable presence in the international conferences and schools on commutative algebra. She's an excellent organizer, and I can affirm that. So her expertise is evident in her numerous talks worldwide, and you will witness one today. Alongside with her academic activities, she has authored a substantial body of work on prestigious journal reflecting her enduring contribution. And one very interesting aspect of her academic career, she has served as the local leader of Piano Laurie Scientific Project since in 2012, and has coordinated European project in Erasmus K2 and focus on student with mathematical learning with disabilities. So this is a very interesting contribution to the society, toward the society, and demonstrating her commitment to inclusive education. So over to you, Manuela, and this is very inspiring. And not many mathematicians are so much diverse in different societal and upbringing of or in toward inclusive of everyone. So that's wonderful work you are doing. And over to you on on this particular seminar today. She will be talking about Cartwright-Sturmfels ideals of graph and linear spaces. Over to you, Manuela.
Okay. Thanks, Imran, for your nice word and also for speaking about this kind of activities that I really love about inclusive mathematics. And so thanks very much. And thanks to all the organizer for inviting me to give a talk in this very, very nice seminar series. Okay, so today I'm going to speak about some results obtained jointly with Aldo Conca and Elisa Gorla. And it was really a very long research project. So as you see, we wrote 5 papers about these arguments in 7, 8 years of work. We are still working on it. So I'm very happy to explain to you more or less what we did about it. So for the first part of the talk, I'm going to really introduce basic facts in commutative algebra. So I apologize for people who know it, but I think it's important that everybody knows the notion I'm using and also to fix the notation. So hope not to bore anybody. Okay, so we start just by a very simple facts about term orders. So what is a term order? So we always work over a field K, and we will consider R a polynomial ring in n indeterminates. And a term order is simply a total order on the set of the monomial of R, and we want to have these 2 properties satisfied. Every monomial has to be strictly bigger than 1, and the order has to be behave well with respect to the multiplicative structure of the ring. So if n is less than m, also n times t has to be less than m times t. And there are many term orders, and the 2 most important classes of term orders are these 2. So fix an order on the determinants. So assume x1 is bigger than x2 and so on, bigger than xn. The lexicographic order is simply the alphabetical order. When you assume this, think to the determinant as letters and use the alphabetical order. And the reverse lexicographic order is different. This time we start comparing the 2 monomial from the hand. So we say that m, monomial m, is bigger than m prime if and only if the degree of m is bigger than the degree of m prime, or this is the case we are interested, if the monomial have the same degree. We have to compare the 2 exponent vectors. So we take the vector b minus the vector a, and we look at the first non-zero component starting from the right, and we want that this is bigger than 0. Just to understand it better, we see an example. Okay, so if you use lex, x1, x4 is bigger than x2, x3 because x1 is bigger. So it's like the A, the first letter of our alphabet. But if you use revlex, x2, x3 is going to be bigger than x1, x4 because x1, x4 has x4, which is a smaller indeterminate appearing in it. So these are two different order, which depends on the order in which you write the indeterminate. Why are we interested in term ordering? Okay, so when we have a term order, then we take f, an element of our polynomial ring, and we can write f as a linear combination of monomials, clearly. But now, since we have the order, we can assume that M1 is bigger than M2, bigger than MS. We have a unique way to write this polynomial now, according to this order we have fixed. And then we can say, we call initial monomial of f, the biggest monomial appear in F, which in this case is M1. Okay, so example, just to understand better. So take just this polynomial ring in 4 variables. Assume x bigger than y, bigger than z, bigger than t. So if we take this polynomial f and we fix Lex order, then we write it in this way because the biggest monomial that appears is x2 to the z, thanks always to alphabetical order. And then it comes x, y, z, and then y to the 3. So according to Lex, we write f in this way, and the initial monomial of f is x to the 2z. But if we use revlex, now the biggest monomial is y to the 3, because it does not involve z. And the other two monomials involve z. So then it comes x2 to the z, and then xyz. xyz is the smallest now, because it contains the z and also y. Okay, so in this case, the initial monomial is different, is y to the 3. So, okay, so now, given any polynomial, we can get the initial monomial, and we want to do it for an ideal. Now, if we have an ideal in the polynomial ring, we define the initial ideal of I with respect always to the order we have fixed to be the ideal generated by all the initial monomial of all the elements in the ideal. This is important, not only of the generator, we take all the elements in the ideal. For everyone, take the initial monomial and take the ideal generated by all these monomial. Now, the very important ideal in commutative algebra, very important technique to prove is this one. We have our ideal I, we consider the initial ideal. The initial ideal is really easier to be studied because it is a monomial ideal. Monomial ideals are really easier to be studied. We can associate to them some combinatorial object, but also just to understand, if you need to know if an element is in a monomial ideal, it's enough to see if it is a multiple of one of the generator. But if you want to know if an element is in an ideal, this is more complicated. So monomial ideals are really easier to study. So the idea is, okay, I have I consider initial ideal with respect to some term order, and then I can deduce many information on I by studying the initial ideal, which is easier to study than I. And which kind of information are we interested in commutative algebra? So from now on, just consider the case in which the ideal I is homogeneous. What I mean, we can give degree 1 to all the indeterminates on R. So this is what we call the standard grading. And then every monomial has a degree. And an element is homogeneous if it is the sum of monomial all of the same degree. And an ideal is homogeneous if it has a system of generator of elements which are homogeneous. So from now on, we always consider ideal generated by homogeneous element. And we want to do it because then when we pass to the quotient is graded. We can write R mod I just as the direct sum of the part of degree T of R mod I. And then we can consider the Hilbert function. The Hilbert function is the numerical function that associates to T the dimension as a K-vector space of R mod I in degree T. So all these graded components are K-vector space of finite dimension, and so we consider all this dimension. And this is a very important invariant. This gives many informations on I. And to have in a compact way, we consider the generating function, generating series, sorry, of this function, which the so-called Hilbert series is exactly this series. Okay, and it can be proved that this series is always rational. So can be written as the h of z, which is called the h polynomial of the ring, divided by y minus z to the d. And if we assume that h of 1 is different from 0, there is a unique way to write it. And this d, it turns out that it is the Krull dimension of the ring. So to know the Hilbert series allows us in particular also to calculate the Krull dimension of the ring. And the values of the h polynomial in 1 is the so-called multiplicity of the ring. Also, the multiplicity gives a lot of information on the ring. Okay, so these are some of the invariants we are interested in when we study ring, a commutative ring. And the very nice fact is that, as I said, if we know this kind of information for the initial ideal, I don't write now, when I don't write the term order, it's just because, I mean, fix any term order, calculate the initial ideal. And if we know the information for the initial ideal, we can get it for the ideal itself, because the dimensions stay the same, the multiplicity stay the same, and also the Hilbert series stay the same. So as I said to you, I calculated for the initial ideal, and I have it for free also for the ideal itself. And moreover, the graded Betti number, which are the invariants related to the minimal free resolution of the ring. If you don't know what it is, it's the same, but it's again something very important for people in commutative algebra. The Betti number don't stay the same, but they can only increase when we pass to the initial ideal. So if you can calculate it for the initial ideal, we have a bound on the Betti number of the original ring. And also, other very general philosophy is if the initial ideal is good, also the ideal is good. Where good means, for example, if it is radical, the initial ideal is radical. If the initial ideal defines a Cohen-Macaulay ring, also the starting ring is Cohen-Macaulay and also Gorla. Again, if you don't know what is...
I have a question.
Sorry?
I have a question. So is there any specific criteria where the equality for Betti numbers hold?
Yes, thanks for the question. We will see some classes in the following. There are not such a general, it's a strong fact that the Betti numbers stay the same. There are some rigidity theorem, like if it is happen for a certain Betti numbers, then it happens also for other Betti numbers under the assumption that the initial ideal is square free. But in the following, we are going to find nice classes of ideal for which this equality holds. Thanks.
Okay, thank you.
Okay, so as I said, if we know something about the initial ideal, we get information about the ideal. But as usually in mathematics, there is a price to pay. And in this case, the price to pay is that it's not so easy to find the initial idea in general. Okay, it's not clear. So we start with I. We have a nice, maybe a nice system of generator of I. How can we find a nice system or generator of the initial idea? This is not clear. In fact, unfortunately, or fortunately, because things are more interesting, it is not true that if we take the initial monomial of the element of a system of generator of I, we get the system of generator of the initial ideal of I. These are not enough. Okay, to convince you, I show to you this example, very simple one, polynomial ring into variables. As order, we just take x with x bigger than y. So if you take I generated by these two polynomial, x to the 2 plus y to the 2, and the other one is xy, if we take xf1 minus yf2, we get x to the 3, which is in I. So the initial monomial, which is itself, because it is a monomial, it is in the initial ideal of I, but it is not in the ideal generated by the two initial monomial, which are, for f1, we get x to the 2, and for a2, x2, we get xy. Okay, so this proves that the initial monomial of f1 and f2 are not enough to generate the initial ideal. What we have to do, we have to add this x3 as a generator. X3 as a generator is not minimal, is not necessary, but if we want to add the generator of the initial ideal, we have to add it. So, and one can see in this example that if we add x to the 3 as a generators, as f3, then at this point we have also all the generator of the initial idea. So when this happens, so we say that we have a Grobner basis. So this is a really very important concept in commutative algebra. It comes from the computational algebra, but it is very strong, powerful tool also for theoretical results. So we say that a set G1, GR is a Grobner basis of an ideal with respect to term order, so always fix a term order, if the initial monomials of G1, GR generate the initial idea. Okay, so if you think to the example before, we needed the initial monomial, we needed f1, f2, and also x to the 3. But in general, it is easy to see that if we have a Grobner basis, for sure we have a set of generator of the ideals. But the opposite is not true, the converse. We have just an example. But the good news is that there is an algorithm. We are not dealing with it, but it's important to know. There is an algorithm, the well-known Buchberger algorithm, which gives us a Grobner basis starting with any set of generators. And the idea is that one add sometimes one have to add many elements to have a Grobner basis. But at the end, one get a Grobner basis. But the nice situation is the one in which the nice set of generators is a Grobner basis. Because if we have to add many complicated objects, then the initial ideals becomes very hard to be studied. We don't have control of it. Okay, but now I want to ask more. So to have a Grobner basis.
Can I ask a question?
Yes. Hi, Sudhir.
Yeah, Emanuela, hi. In the previous example, why is x cubed not in the initial ideal? Maybe you want to change the order of the variables and make y square and xy as the, because x square is there, right?
Sorry. You are right. It was not what you wanted.
I think if you just change the order of x and y and
make x and y, yes.
Yeah, and then make it y square xy. Yeah.
Sorry.
I'm sure you meant that, yeah.
Yeah, yes, sure. Sorry, clearly x to the 3.
Yeah, it's okay. Yeah.
I have to take
Anyways.
x2 minus yf1. Sorry.
Yeah.
It is xy to the 3, right?
Yeah, just a typo, I think. Yeah.
Yes. Sorry. Thank you, Sudhir.
No problem. Yeah, good to see you, Emanuela.
Thanks.
Okay.
Thanks a lot. Okay, so now I want to ask more. All what I said until now strongly depend on the term order. But now I want to ask that to have a set which is a Grobner basis with respect to every term order, which is really more, this is what we call the universal Grobner basis of an ideal. So we say G1, JR is a universal Grobner basis of the ideal I, if it is a Grobner basis with respect to any term order. Okay, so the initial ideal is generated by the initial term, by the initial monomial of G1, GR with respect to every term order. This is very strong because, as I showed you before, if we change term order, the initial monomial change. I'm not saying that the initial monomial is always the same. The initial monomial of G1, GR are different, but with respect to every term order, they generate the initial idea. So this is a very strong fact. Again, I want to point out that every ideal has a universal Grobner basis. This is not trivial. This depends on the fact that there are infinite term order, an infinite number of term order, but just a finite number of initial ideal. This has been proved many years ago. So you can calculate the initial ideal with respect to many term order. After a while, you don't get any new initial idea. So if we take this finite number of initial ideal, for every one of them you take a Grosvenor basis, the union of this Grosvenor basis is a universal Grosvenor basis. But usually it's a very huge basis, and it is very bad, it's very hard to handle for it. So what we want is to have a natural universal Grosvenor basis. But I mean, the best possible, and we will see that sometimes we will have it, is to have a system of generators, a minimal system of generator, which is also a Grosvenor basis. Very rare, but it happens. Or also, it's also good if we have a nice description of the universal Grosvenor basis, which is not just the union of many Grosvenor bases, a universal Grosvenor basis which have a very nice structure. And when we have universal Grosvenor basis, we can calculate many initial ideals, and so this is really convenient. It's really, really nice. Okay, and one more definition, then after it I go to study the class of ideals I want to study, is the definition of generic initial ideals. So the idea is always the same. We want to pass to an initial ideal, but we want to think it as it is in a generic coordinates. Let me say, this is the idea. So what we do, we consider the element of GL n of k, call it G, one of this element. And so this is clearly can act by linear substitution on the polynomial ring. So we can change the coordinates according to G. We can consider G of I for every ideal I, and then we can calculate the initial idea. Okay, so now we have many initial ideal because we take I, we take G, we calculate G of I, and then the initial ideal. And the important things, this is why I call this theorem definition, it has been proved that the outcome is almost always the same. In almost always, I mean there is a Zariski open set for which for every G in this open set, this initial ideal is the same. And this is why we call it the generic initial ideal. Generically, in generic coordinates, this is the initial ideal we get. And why this is especially nice initial ideal? Because it has this strong property. Every generic initial ideal is Borel fixed. Borel fixed means that it is fixed by the action of every element in the upper triangular invertible matrices. More explicitly, if the characteristic of the field is 0, Borel fixed means monomial, and this exchange property has to hold for every monomial in the ideal. But if xi divides m and j is smaller than I, then we want to have xj times m divided by xi in j. Okay, and if the characteristic is positive, there is a similar condition. And to have Borel,
is this a strongly stable idea property?
Exactly. If the characteristic of K is 0, it coincides with strongly stable. Exactly. Yes. But if it is P, no, it's different. It's what is called P strongly stable. Okay. It's exactly the same. If the characteristic is 0, Borel fixed is strongly stable. And since this generic initial idea has this structure, it is easier to study it. For example, we have a very nice description of the resolution, which is the Elia-Hooker-Verre resolution. And clearly, since we obtained the generic initial ideal by doing a change of coordinates and then the initial ideal, we also have that the Hilbert series stay the same. So all the invariants we saw before, the dimension, the multiplicity, they just stay the same. So it is, again, very interesting to do it, to have it, very hard to describe it in general, because it's not easy to find the initial ideal is okay if you have a Grosvenor basis, but the generic initial ideal is harder to find. Okay, now we have, I hope it's okay, it's all clear. It took some time, but I think it was important to have all the tools. And now I introduced the rings that were the starting point of our job, which are determinantal rings. Okay, so what are determinantal rings? Take a matrix of indeterminates, and take R, the polynomial ring, which has indeterminates the entries of the matrix. And then if we fix T, an integer T, we can consider the submatrices of X of size T. So fix T indices for the row, T indices for the column, take the submatrix and take the determinant. And this is the so-called T minor. And the determinantal ideal is an ideal generated by the T minors of the matrix, and the determinantal ring is R mod this idea. Determinantal ring are very classical object. They are been studied by many people from an algebraic point of view, from a geometric point of view. And these are just the most classical family, but there are many other family ideas generated by Pfaffians of skew-symmetry matrix, minors of symmetric matrix, ladder, subregion. So there is really a big world. But we want to focus on this one today, just ideas generated by minors of a generic matrix, and particularly on Grobner basis. And it was proved by Sturmfels in the 90s that the T minors are a Grobner basis with respect to any diagonal order. A diagonal order is an order that selects in the minor as a initial monomial the main diagonal, the product of the indeterminates on the main diagonal. But, so this is very nice because it's one of the situations I said to you before. The natural generators are also a Grobner basis, but they are not a universal Grobner basis. If we take an order which is not diagonal, it's not true anymore that they are a Grobner basis. But for special cases, if we take the two minors, so the smallest minors possible, okay, the one minus one just indeterminates are not so interesting. We take the two minors. Sturmfels and then Villarreal proved these very nice results. The generators are not a Grobner basis, a universal Grobner basis, but there is this nice combinatorial description of the universal Grobner basis. I don't want to go in the details, but as you see, this is a combinatorial description depending on complete bipartite graphs. And moreover, they also proved that all the initial ideals of I to X are radical with respect to any term order. But the best situation is the opposite one. We have the smallest possible minors. We have the biggest possible minors, the so-called maximal minors. Okay, so what is a maximal minors? If the matrix has sites m times n with assume m is less than or equal to m, the maximal minors are just the minors of sites m. And in this case, there is very, very nice results, always in the 90s, in two papers, one Bernstein and Sturmfels, and the other one Sturmfels and Zelewisky. And they prove that the maximal minors themselves form a universal Grobner basis of the idea. So this is really, as I said before, the best situation where the maximal minors are a minimal set of generators, but they are also a universal Grobner basis, a Grobner basis with respect to every term order. And the two papers are very long and very complicated, contains a lot of interesting facts that the authors use to prove it. And moreover, some years later, Bucher proved, and this is one of the first answers to the question I got before, for these ideals, the Betti number stays the same when we pass to the initial ideal with respect to any term order. And in particular, the resolution is linear, which is, let me say, the best possible resolution, just one shift in every position, and the shift, every shift is one more the previous shift. So this means really these ideals are very, very nice. And in the same paper, Bucher wrote also generalization. He proved that the same statement, so the universal Grobner basis statement and the fact that the Betti numbers stay the same, also if instead of taking a generic matrix, all matrix of indeterminates, one puts some zero, not in any position. He gives precise rule where you put the zero. Okay, and this was really the starting point of our job, our work, because we realized that there was a way to reproof the result of Sturmfels and Zalewiski and Bernstein in a very simple way. And our question was, okay, maybe we can prove a similar result. So universal Gromner basis and Betti numbers that stay the same for matrices of linear forms. So instead of taking indeterminates or zero, we want to consider a matrix in which we put as entries any linear form. Okay, so this was our starting point, and I show you an example, very simple one, which says that one cannot hope to prove really the same result. In fact, just take this matrix, which is almost generic because it has indeterminates everywhere, and just in this position, it is x1 plus x6. So this is really just obtained from a generic with the change of coordinates. So one say, okay, what can be bad? What can go bad in this situation? And it can, because one can prove that for almost all the term order, the two minors are a Gromner basis of the ideal that they generate. And note that in this case, they are two minors. They are also maximal minors. But if we take any order with x1 bigger than x2, bigger than x6, the two minors are not anymore a Gromner basis. We always need at least a generator in degree 3. So in this case, very simple, very similar to the generic case, the two minors, which are the maximal minors, are not anymore a universal Gromner basis. So this was a little bit discouraging, but what we realized is that we have to work not anymore with the grading, but with the multigraded structure. Okay, this to obtain some results. So this are the matrices we were able to deal with. We consider matrices of linear forms, which are column or row graded. I show you the definition, but also an example, which is always easier to understand. The idea is now, we give to the entries, to the indeterminates, not a grade as before, 1, but a multigrade. So we say that the degree of xij is ej, where ej is just the vector, the jth vector of the canonical base, 0, 0, 0, 1, 0, 0, 0. Okay, so to every indeterminates, you give a multigrading. So all the object in the ring becomes multigraded. And we say that the matrix is column graded if the elements in every column has the same grading. What does it mean? So we can see in this example, if in every column, the elements are linear forms, also 0 are allowed, but just involving determinate with the j's, with the second index equal to the number of the column. For example, in the second column, we have just indeterminate with j equal 2, and so on. In the third column, only indeterminate with j is equal 3, and so on. You see, we can also allow the repeated entries, no problem, 0 everywhere where you want, but this is what we mean by column graded matrix. And analogously, we can consider the row graded. Okay, in this case, as you see here, in the first row, the indeterminate that appears, they have I equal 1. And in the second, they have I equal 2. And then every linear form is allowed. Okay, so in some sense, these matrices, they seems also more general than the one in the example I showed you. I showed you this example in which things are working not so good. But this multigraded structure turned out to be the good things to consider. Okay, and what we proved, this was our first paper, was that for the maximal minors, so if you take L, a matrix column or row graded, we proved that the maximal minors is an ideal which is always radical. It has always linear resolution. The initial ideals for every term order are radical and have linear resolution. And also the Betti numbers stay the same. So all the nice property that holds in the generic case also holds for this case in which the matrix has column or row graded. And in the case of the column graded, we will understand better why. The two cases seems the same, but not, they are very different. And in the case of column graded, we have the best possible things. The maximal minors form a universal Grobner basis. In the row graded case, this is not true, but we can say that we have a universal Grobner basis of element of degree 1, 1, 1, 1, 1, 1. So a good, a nice, so the degree don't become too high when we take a universal Grobner basis. And we also had some results for two minors. The first are similar. The ideal of two minors of column or row graded matrices are radical. And also all the initial ideals are radical. And again, we have a result on the universal Grobner basis, on the degree of the universal Grobner basis. Also in this case, the generators are not the universal Grobner basis. We could not hope it because it was not true in the generic case, but we have a universal Grobner basis of elements which have multi-degree bounded by 1, 1, 1, 1. So this was our starting point, and we were very happy because this generalized the result of Zelevinsky, Sturmfels, and Bernstein, and in a nice way, and the proofs were not so complicated. But then, as it happens very often in mathematics, I speak especially for young people, now when you have a proof which is nice, it's a good idea to try to understand why it works. So we really try to understand which property of this ideal was the property we used. So it was independent in a sense from the fact that we were studying minors. We realized that we were really using a lot this multigraded structure, which clearly we can put this structure also on other ideas. So after we did it, we thought a lot about it, and we realized which was the point. Okay, and this allowed us to consider a very more general situation. And so again, as I said, we really realized that the multigraded setting was the right setting to work with these things. So now forget for a moment about minors or matrices. We just call S, again, a polynomial ring. I just changed the name because I think now to a multigraded polynomial ring. Okay, so I still call the indeterminates with two indices because I want to say that I give degree EI to the indeterminate Xij for every j. Okay, so I have many different set of indeterminates which have multigrade depending on the first index. And now I want to live in this multigraded setting, not anymore in the standard graded setting we are used to. So we have to little bit, at the beginning it sounds a little bit strange, but things work as in the standard graded setting. So we can consider homogeneous ideal with respect to this multigrading. So ideals which are generated by element which are homogeneous with respect to this multigrading. And so this ideal are a direct sum of their multigraded part. And also we can consider the Hilbert series. Now the Hilbert series is multigraded too. It's not anymore a series just in the Z, just in one indeterminates, but is a series is more indeterminates. And it is the generating series of the Hilbert function, but now the Hilbert function is the dimension of the multigraded part of the ideal. Okay, it's all the same, but all multigraded. And this is really the main tool we are going to use. We can consider the multigraded generic initial idea, exactly in the same way as we defined before, but now we allowed only change of coordinates, only element of GL and K that respect the multigrading. Okay, everything we use now has to respect the multigrading. So when we do this change of coordinate, they have to always to respect the multigrading. I can change one indeterminates with a sum, with a linear combination of other with the same multigrade. All has to be multigraded, but everything works exactly in the same way. We can define this multigraded generic initial ideal. So from now on, when I write a gene, I always mean the multigraded generic initial ideal. And again, this ideal is Borel fixed, but now in the multigraded sense. Okay, as we said before, there was this definition, this strongly stable definition. Now we can substitute an indeterminate by another one, but just if it is in the same multigrade. And also, clearly, as before, the multigraded Hilbert series of I is the same as the multigraded Hilbert series of the generic initial ideal. Okay, so everything works, but why we consider a multigraded setting? What happens is that the multigraded structure is more and more rigid than the graded structure, which seems worse, but it is good at the end because it helps a lot to have more control on the situation. Okay, so now I'm really arrived to the Cartwright-Sturmfels ideal, which were in the title. Looks a lot, but now I give to you the definition. So, as we said, we have S, this multigraded polynomial, and we also need for the definition of this subring of S, consider T the subring of S, which has one indeterminate in every multigrade, just x11, x21, xv1. Okay, but the ideal we consider, so this class of Cartwright-Sturmfels ideal, we denoted by CS, is the set of all the ideal of S. We are living in the polynomial ring S, whose multigraded generic initial ideal is radical, so it is square free for some term order, and we prove that if it is true for one, it is true for all term order. And this is a theorem, is not at all clear, but there is another way to see it. It is the set of the ideal, which has the multigraded Hilbert series of some radical Borel fixed idea. Okay, these are two ways to define it. Both it is equivalent, and both are very useful. And we also defined another class, which we call CS star. Now I'll say shortly why CS star, which is again we have two possible ways to define it, using the gene or using the Hilbert series. And this is the class of the ideals such that the generator of the generic initial ideal are in that ring T. Only involve this indeterminate, again for some term order, but it is equivalent to ask that it is true for all term order, or we can see them as the ideal, which has the same Hilbert series of an ideal J. This time we ask that J has generators just involving the element of T. So this class of ideals are very special, but they are also very nice. Okay, and what we were...
excuse me, Emanuela.
Yes.
What's the role of S and T in the definition?
Okay, thanks. The ideal, when I write the class of ideal in S, I just use T to define the class CS star. Because, okay, but thanks. This is an important point. In CS star, I take the ideal of S, but which has this very strong property. When I calculate the generic initial ideal, it turns out that the generators live in T. But the ideal is still in S.
Okay.
It's just to define the class CS star. But thanks. But the ideal I'm studying, they live all in S, in the big multigraded polynomial ring. It's only, okay, maybe you don't need it. We can also just say CS star is the ideal whose generator of the gene involve only one indeterminate in every set. Okay, it's just a way to see. Okay, just clear all. No, I thank you, because this is important. It's just, but the ideal I'm considering are in S. I never start with an ideal in T. I just check it for the gene and for the J. Okay, it's clear for the rest? Okay, so first thing we were able to prove is that if we have an ideal in CS or respectively in CS star. Also, the initial ideal is in CS, respectively in CS star. And the nice thing is that this is also more important. The J in the definition of CS and of CS star, so this radical Borel fixed ideal for the CS and this ideal whose generator in T for the CS star is forced to be the generic initial ideal for every term order. So this is the very strong fact. So if we found an ideal, concentrate for a moment on CS, but the same is true for CS star. If we have an ideal with the same Hilbert series of I, and this ideal is radical and Borel fixed, we are sure that this is the generic initial ideal for every tau. This is not true at all in the standard graded case. This is really something due to the fact that we have a multigraded structure. So we just write G of I because it does not depend on the term order. This is really something strong and not usual at all. Another nice thing is that these classes are closed under many algebraic operation. You can do intersection, colon, some quotient, and you are still in the class. So if you have some ideal in the class, we can build many other ideals in these classes. And why I call it C star is because there is a duality between the two classes. Only if I take square-free monomial ideal, I have that I is in CS if and only if its Alexander dual is in CS star. I'm not going to define Alexander dual. It's a concept coming from simplicial complexes. So if you know it, I think you appreciate the fact that there is this duality, and this duality is very useful to prove facts. Okay, so now we have these two classes, which are very special, and but also very nice because they have all this nice property and some other that I show. They are very special, but we have ideals for which are CS or CS star. In particular, the idea I spoke before. So if we take L, a matrix which is row or column graded with entries in S now, then the ideal of the two minors and the ideal of the maximal minors are in CS. So this was the property I said you before. We proved those facts we saw before about this ideal, but we realized that what we have used really was the fact that this ideal had this property, are in this class CS. And moreover, if L is column graded, you remember this was the best case, the case in which we had the universal Gorla basis. The ideal generated by the maximal minor is also in CS star, which is in some sense the best classes. Okay, so this is the first class we had. So this was really the starting point. But then clearly we wanted to write what are the properties of ideals in CS and in CS star. And so this is what we are able to prove. If I is an ideal in CS, it is radical and all its initial ideal are always radical. And moreover, we have a bound on the generator, on the degree of the generator. Every minimal generator has multi-degree less than or equal to 1, 1, 1, 1, 1. And we have a very nice bound on the regularity, on Castelnuovo-Manford regularity. Is bounded by V, where V is the number of the grading. And the ideal in CS has also better properties, because for every ideal in CS star, we have that any minimal system of generator of I is a universal Gorla basis. As I said, it's the best possible case, minimal system of generator which are a universal Gorla basis. And in this case, it's true for any minimal system of generators. And moreover, we have a very nice description of the generic initial ideal, which depends, and you see, just by the multi-degree in which the ideal is not zero. Consider the multi-degrees in which the ideal is not zero, take the corresponding monomials, and we have a very nice description of the generic initial ideal. As you see, it involves only the indeterminates in the polynomial ring T, as we saw. So,
excuse me, Manuela, I was just curious to know about the underlying Borel matrix in this particular case. when you are using double indices?
The
The upper triangular
yes,
matrix.
they are block upper triangular
A
matrix.
block upper triangle. Okay.
You have to
Okay.
take it block because you have the multigraded structure respected. You have to have a block for every multigraded part.
Oh, okay. Okay. I was just curious to know. Thank you. Thank you.
Yes, thank you. No, this is a very good question. It's exactly like this. Not all the upper triangular, you have to have block correspond upper triangular, but also blocks corresponding to the multigraded. And also the multigraded Betti numbers, which are the same as the graded Betti numbers, but in the multigraded setting, they stay the same, passing from I to the initial ideal for all ideals in CS star. And moreover, we have also a bound on the projective dimension, which is again V. And in fact, the regularity for the CS, we prove it by using the duality, the Alexander duality, by starting from the fact that we have this bound and projective dimension of S mod I. So these ideals are very nice, have all this nice property that usually ideals don't have. So what we did in the next, our next papers was to find nice other classes of ideals. So we had these determinantal ideals classes, but we wanted to find classes of other kind of classes, and we found some. So we proved, we studied binomial edge ideals, and we proved that binomial edge ideals of any graphs are in CS. And we generalize the results of previous authors. And when we studied some ideas coming from multi-homogenization of linear forms, and we proved that these ideals are in CS, and in some special cases, they are also in CS star, so in the nicest classes, and this again generalized results, very nice results of Ardila and Bucher. And then we also found that multiview ideas studied introduced by Haholz, Sturmfels, and Thomas, they are also in CS, so they also have all these nice properties. Okay, I don't have time, I think, to explain to you which, to give the definition of this kind of object. What we like it, they are really ideas coming from different world. And we are looking for more ideas with such CS on CS star. I think here there is space to work also for young people. So if you have a nice class of ideas which are radical and which have that nice properties, maybe they are CS or CS star. And if you find it, you can create other ideas by the algebraic operation. So this is more work to do on it. Okay, this was I wanted to say. Thanks for the attention.
Thank you very much, Emanuela. Thank you.